right, we are going to look at 8.2, constructing intervals for proportions. We started 8.1 talking about kind of the generic how to construct a confidence interval. And we talked about that we take the point estimate and we add and subtract this thing called the margin of error. So we're going to get more specific now, and we're going to talk about how to construct an interval for proportions specifically. So we're going to kind of put means to the side for a bit, and we're going to talk about proportions. So before we start, we're going to review a few things. So what point estimator do we use to estimate a population proportion? So remember, our point estimators could either be p hat, x bar, or s sub x. Those are going to be our statistics that we use to estimate the population values. So for proportions, p hat estimates p. P hat estimates p. Now, for the mean of our sampling distribution of sample proportions, this is the mean of p hat, that just equals the population parameter of p. That's normally given to us in the problem. The standard deviation of the sampling distribution of p hat is, the standard deviation of the sampling distribution of p hat is the square root of p times 1 minus p divided by the sample size. Now, for those of you who are maybe following along here, you would know that we might have a problem because I told you guys at the beginning of chapter 8 that we were no longer going to know what the population proportion really is. So how are we supposed to use these formulas if we don't know p? We're going to talk about how to deal with that today. Remember that when we do the standard deviation of the sampling distribution, we always check the 10% condition. And in order to check the 10% condition, you check to make sure that 10 times the sample size is less than the population size. Just to kind of show you guys this formula rearranged, that would mean that 10 is less than 1/10 of the population. That's why this is called the 10% rule. I need to make sure that the sample size is less than 1/10 of the population. And here in just a little bit, I am going to talk more about why that is. And I'm going to give you the full story on where this comes from and why we check it. All right. Now, how do we ensure that the sampling distribution of sample proportions is approximately normal? So probably you remember that we check the large count condition. And to do that, we checked that n times p had to be greater than or equal to 10, and n times 1 minus p had to be greater than or equal to 10. Same thing on this. We have p in this problem here, or in this condition, and so we will talk today about how to deal with the fact that we no longer get p. And here it is. Since we no longer have the population parameter of p, we need to replace it with the sample proportion of p. So basically, guys, anywhere in these formulas that you see a p, if we don't know the actual population value of p, then we're going to replace that p with the p hat, the sample proportion. That's going to be the sample value that we are estimating, okay? And so the reason that we're doing that is because p should be a good estimate of the true value of the population. And so if it is a good estimate, a good unbiased estimate, then we're going to go ahead and use it since we don't know the true population value. And so anytime you see p in these formulas, basically you'll just replace them with a p hat. You'll even see on the formula chart, so these are the formulas that you guys have been using for chapter 7, you'll even see that it shows you right here that if we don't know the true population p, we're just replacing it with p hat. Now there is a terminology difference. If we're using the estimate of p, if we're using p hat, the sample proportion, then we call that the standard error instead of calling it the standard deviation. It's just a terminology to indicate that, hey, this is the standard error. We're pretty sure that it's a good estimate of the standard deviation, but there could be some variability in it. And so we call it the standard error to indicate that p hat was used instead of p, okay? It even tells you this on the formula chart, that the standard error is an estimate of the standard deviation. And if the standard deviation of the statistic is assumed to be known, then you should use the p instead of using the p hat. But most of the time, we're not going to know it because that's what we're estimating. So basically, all of these formulas are going to be the same. We're just going to be using p hats instead of p's. That's going to be the same for our large count condition as well. We'll just stick a hat on the p and move forward. All right, so let's now look at the general form of a confidence interval for population proportion, and then we're going to turn it into the specific formula. So we have the point estimate plus or minus the margin of error. So our point estimate is our statistic. It's our p hat. Okay, so this is p hat. That's the value that is going to be right in the middle of your interval. And then you're going to add or subtract the margin of error. Now, the margin of error is actually made up of two things. It's made up of something called the critical value and then the standard error. And that's what we just talked about, the standard error being the standard deviation formula, but using p hat instead. So the standard error part is the p hat, 1 minus p hat divided by the sample size. So the only thing then that we kind of don't really know about is this thing called the critical value. What that is this is something called the z-star critical value. What this is this is the z-score that tells how many standard units to go out from p hat in order to capture the percent of data needed to be C% confident. So basically what z-star is it's a multiplier. It tells us how many of these standard errors we're going to go from the p hat estimate that's in the middle, so that we can capture the percent of data that we're looking for in order to have that level of confidence. We'll talk more about that in our next video, but for now, just know that z-star is a z-score that is associated with how confident we want to be. Okay? Now, back to this formula. I'm going to rewrite the formula again. The formula has three parts. P hat plus or minus the z-star critical value times the square root of p hat 1 minus p hat divided by the sample size. So it has three parts. It has the p hat part, it has the z-star critical value part, and then it has the standard error part. Each part has a condition that has to be checked in order to ensure that it is in fact valid. For p hat to be an unbiased estimator of our p, we need to check to make sure we have a random sample. So to ensure p hat is an unbiased estimator of p, we must have an SRS, a simple random sample, from the population. Okay? So basically, that's something that's pretty easy to check. It's going to basically tell us that in the problem, and so that's going to be one that's just going to pretty well most of the time occur. The second thing is we need to ensure that we can use a z-star critical value. The only way we can use a z-star critical value is if we have a normal distribution. So to ensure z-star critical values can be used. Check the large count condition. So you guys already know how to check this. We need to make sure that n times p hat is greater than or equal to 10, and n times 1 minus p hat is greater than or equal to 10. We're going to check both of those. If both of those pass, then we are for sure guaranteed to have a normal sampling distribution of p hat, and so z star can be used because z scores come from a normal distribution. And then our third one is one that we've been checking, and it is our 10% condition. Now, this is where I'm going to explain to you why and all of that good stuff. So, the reason we check the 10% condition is for the condition of independence. Independence. So, this is to ensure our sample has good variability. We check the 10% condition. And again, that is just 10 times the sample size has to be less than the population size. Now, let me explain. So let's just say we have this population here, okay? And in this population, we have little groups that make up this population, okay? All of these little subgroups, maybe think of like the city of McKinney, and maybe these are little neighborhoods in this population, right? Most of the time in most neighborhoods, you kind of have like similar demographics, maybe similar type houses, similar opinions, things like that. Okay, so let's say we have our population, we have all these little pockets of similar type things in the population, or similar type demographics or neighborhoods or whatever. So we start taking our random sample, okay? So we start sampling, okay? We're getting pretty good variability, right? We're getting a little bit out of every pocket in our population. Now, if I take too many people out of the population, I start to sample too much. I start to get to be more than about 10% of the population. You can start to see what can happen. I start to possibly go back to the same neighborhood. Look at this neighborhood right here. And now I've got too much of representation out of that particular neighborhood. I no longer am getting a good variability out of my population. I'm starting to get a little bit of repeated thoughts. This is something called groupthink, basically, where these people kind of have a similar opinion, and because I took too much of a sample, too big of a sample, I've gotten kind of repeated opinions. They're all kind of thinking similarly, and so that's not a good thing. And so in order to combat that, I want to make sure that my sample is no bigger than 10% or 1/10 of my population. That ensures that I'm not getting little pockets of bias. So this is why we want to make sure that we are not taking too big of a sample, no more than 10% of our population. That goes with our standard error part of the formula, because standard error is the variability in the sample, and this goes along with why we want to make sure we're not taking too big of a sample. We want good variability in the sample. So that's why we check the 10% condition. All right. We call it the independence condition because we're making sure that each subject in the sample is independent of every other subject or every other person's opinion. Okay? So those are our three conditions: random, normal, 10%, or independent condition. Random is to ensure that we have an unbiased estimator from p hat. Normal is to ensure we can use a z-star critical value. And then independence is to ensure that we have good variability in our sample. Okay? You can check them in any order. Honestly, I usually check them in the random, independent, then normal order, but you can check them in any order. Okay? All right, so let's just do a couple of practice problems to see how to check these conditions. All right, Ms. Lakey's second period class wanted to construct a confidence interval for P, the true proportion of red beads in the jar. The class shakes up the jar and takes a random sample of 100 beads, of which 38 are red. Check to see if the conditions are met. So we're going to check the random condition. We have a simple random sample of 100 beads. So we're good to go on that one. That ensures that P hat is an unbiased estimator of P. Now we're going to check the independent condition. Again, this is I'm just used to checking it in this order. We need to make sure that 10 times the sample size is less than the population. So 10 times 100 is 1,000. That is less than the population of beads in the jar. For those of you who don't believe me, there are 2,155 beads in the jar. I wonder what proportion of them are red. Normal. We're going to check the normal condition by checking the large count. We're going to check the large count condition. We need to make sure that n times p hat is greater than or equal to 10, and n times 1 minus p hat is greater than or equal to 10. So we've got 100. Now p hat, this is the sample proportion of red beads. So 38 out of the 100 beads were red. And so that means that we have what's called success. We have 38 successes. 38 of the beads met the qualification that they were red. So 38 of them are red. And then 100 times, if 38 of them were red, then that means 62 of them were not red, or failures. So that is 62, and that is greater than 10. So we can now say that our sampling distribution of p hat is approximately normal. This checks all of our conditions, so all three parts of our formula will work whenever we're ready to construct our confidence interval. Okay, next problem. Cristiano Ronaldo is currently the most followed account on Instagram with about 540 million followers. Coach Ramos wondered what proportion of Ronaldo's Instagram followers are American, so he selected a random sample of 500 of Ronaldo's followers. In the sample, 308 are American. Check to see if the conditions are met. Random. We have an SRS of 500 of Ronaldo's followers. Okay, so that ensures that p hat is an unbiased estimator of p. Independent, we want to make sure that we didn't take too big of a sample. 10 times the sample size has to be less than the population. 10 times 500 is 5,000, and that is less than the population of Ronaldo's followers, which happens to be 540 million. So I think we have pretty good variability in our sample because we did not take anywhere close to 10% of that population. And now we're going to check to make sure we have a normal distribution for our sample proportion. So we're going to check the large count condition. N times p hat has to be greater than or equal to 10, and n times 1 minus p hat has to be greater than or equal to 10. So n is our sample size, p hat, this is going to be our proportion in our sample that meet the qualification we're looking at. So this is the proportion that are American. So there are 308 out of 500, and so our sample proportion is 308 out of 500, which that is 308. That is greater than 10. And then we have 192 out of the 500 that are not American. And so that equals, that equals 192, which is also greater than 10. So our sampling distribution of p hat is approximately normal. So again, random, p-hat is an unbiased estimator of p. Independent, we have good variability, and we can use our standard deviation of our sample distribution. Normal, we can use a z-star critical value whenever we are ready to do the actual formula. Let's do just one more. Ryan wants to estimate the proportion of the seniors at McKinney-Boyd High School that like the cafeteria food, because he certainly does not. He interviews an SRS of 775 of the 650 seniors and finds that 15 think the cafeteria food is good. Check the conditions. Random, we have an SRS of 75 seniors. That ensures that p-hat is an unbiased estimator of p. Independent, we need to make sure that 10 times the sample size is less than the population size. 10 times 75 is 750, and that is less than the population of seniors. And wait a second, that is not true. So we have a failed condition. The independent condition has not been met. Therefore, we do not have enough variability in our sample. That means that our interval will not be a valid statistical representation of the truth. So what do we do when we have a failed condition? Well, it might seem like we should just stop and quit the problem, or maybe go back to the drawing board and make sure that we don't fail that condition. But here's what we're actually going to do. We're going to proceed with caution. We're going to complete the confidence interval and notate any failed conditions with the final result. Here's the sad thing, you guys. This is something that actually occurs in the real world. So you'll see something like this. So you'll see this big statistic that's written out there on the news or on a billboard or something like that, on Twitter or whatever. And you'll see a little star, a little asterisk. And then down below or at the bottom of the article or the bottom of the news, the TV screen, you'll see a little star and you'll see some writing. And maybe it'll say something like this. Independent condition failed. Results are likely skewed. So they go ahead and tell you that this particular statistic, but then they give you this little fine print that says, yeah, these are probably not very valid statistics. And so the problem with that is that the news will report on the big, giant words or numbers that are on the screen, but they won't read you the fine print. And so you just need to be careful anytime you see an asterisk. It usually means that a condition has failed. Okay, that's where bad stats come from. All right, guys, so there's that. Our next section, we will talk about the Z-star critical value, figure out how to find that, and how to actually put together a confidence interval.